So now we're going to do internal, maybe, depends on how quickly this hour passes, with our one reference frames in gravity. So yeah, I guess I wanted to do this so that we're doing something about gravity and about the gravity gatherings, and really, in some sense, the main motivation of this program can be seen as basically on gravity. Okay, the gauge theories, that's mostly a warm-up. So, I'm going to go back to special relativity again. We're just going to do the same exercise that we did already a few times, but it's also to highlight the unity of this field. So, yeah, first of all, what are the external frame transformations? Or the slash gauge transformations? So here we have lambda nu in SO1 or 1. Now we're going to have small fields. So I have M to M, where M is your space time. So really bulk fields. So excluding again the large ones. And now let's again think about frame orientations. And now I'm going to do a little bit more. So okay, we had we had chosen particular orientation. So again, the tetrad is Lorentz group valued, but now let's note one more thing, that these tetrads, you can view them as maps from your space-time, Minkowski space, to some other space. This M is labeled by the nu, that O is labeled by the frame index. Of course, O is just another copy of Minkowski space, but we can call that a, so we have different in and output spaces. Of course, here M and O are both copies of Minkowski. So we're going to be looking for the same thing now in gravity. So for some reason we always call them R again in some of our papers. And I will again use the same notation I use with gauge theory. I'll write square brackets to highlight that this is a functional. And phi is again some field configuration, just an abstract label. And okay, I guess here I also want to write different in and output spaces. And again, let's do the same thing. So we have, but a slightly more complicated way. In general, okay. In general, it will be some. It will be some neighborhood that maps into some orientation space. And let's call this here local orientation space. And now, what's the analog of having this object being, we want it to be group valued in the ideal case, so you can be more general than what I'm going to say. So just like in the gauge theory case, for simplicity, I restricted to the U's being group valued, but you can actually be more general than that. I just didn't tell you how. So for simplicity, let's also be group valued. So what are we going to do? So this E mu A you can think of it, loosely speaking, as a group value, but really it's like a Lorentz transformation from M to O. So this guy here, you can have to be part of diff from M to O, or N really. So then it's also group valued. By the way, maybe if you want to read about this here in detail, maybe I should give you a reference. That's 206. I'm not sure I remember. It's a very long paper. But there's a warm-up example at the beginning that kind of makes most of this clear. And so at the moment we're again totally classical here. And okay, I told you what gauge transformations are, and then okay, we have again, E maps to lambda E under these external frame transformations. That's the gauge covariance of the frame, which we also had in gauge theory, and which we had in reference frames. And now, how do these guys transform? So what we want is, so I'm looking at the push forward under a bulk diffeomorphism of the field configuration. That's how the gauge transformations act by push forward. And I want that this is gauge covariant, meaning that I get this is F star R of phi. So I just push forward the frame, the untransformed frame. And furthermore, we want that this guy transforms like scalars. So here's Now, what's the next thing that we usually discuss? Relation observables, probably. Relational addressed observables. So here it is SA, and SMU. So what does this do? You can think of it really in some sense as, when you think about the E being a map from M to O, it's in some sense pushing forward the vector S mu from M to O. And so you represent your Minkowski vector now on your rotation, as a vector on the rotation space. And so we can do the same thing here. For simplicity, okay, I'm already using F, so suppose I have some space-time quantity, so it's a functional of your fields, and suppose this is gauge covariant, so it could be a tensor field, so meaning also that A F star phi transforms like F star A phi. And it was more generally than this, but suppose that's true. Then we can define relational observables that describe A relative to R. And okay, I'm going to put some little A to O there. It'll be a little bit more implicit now, but and then what are we going to do? We're going to take that A of phi, which is defined on some, this is, sorry, so A M. So for instance, tensor field on M. And now we're just going to do the analog thing. So we use the frame to push it forward to the rotation space. So this here, for instance, was a tensor field on M, but this is now going to be a tensor field on O. So maybe that's helpful if I do some kind of, so this is our space-time, and suppose this is our region N where that object is defined, and here it maps me to my space O. And really what I'm doing is, this is R, and I'm taking A and I'm representing this here as OA relative to R. And now this is gauge invariant. So if I take that diffeomorphism invariant, that object. So there's a phi here, right? So I can check that. We can look at this OA R. Let me just drop this label here for the moment, and then we look at F star phi. So this will be F star R of phi. Then I take the star here, and then okay, I don't have any space anymore, but then it acts on F star of A phi by this gauge covariance condition here. But then, okay, the first time we have that this is R, then we make use that it transforms like a scalar. So we have that this is phi F inverse. Push forward A. Now I'm really running out of space, but if you have two maps here, and the push forward factorizes, so we get a push forward by F inverse, but the push forward by F inverse is the pullback by F, and that kills this F here. So this is equal to OA R. Is that clear? So that's really the same kind of argumentation that we had in the gauge theory case, okay? So really here we're just making use of the covariance of A and also the covariance of the reference frame. Yeah.
What's the symbol in the OAR for the bar phi?
Oh, this here?
Yeah.
Yeah, maybe for the moment, drop it. So I was going to explain that next. So I call that O. It's like a point O in O.
Okay.
Right. So before we had the gauge invariant observables, there are some functions of X in space time. But now the thing is that these relational observables, they now live in this orientation space. They no longer live in space time. And now let's label them by little O. And yeah, it is a tensor field. So if this was a tensor field on space-time, the rest one is a tensor field on O. And now you can say, really, similarly to what I explained with these with relational observables in gravity, in gauge theory. By the way, I think the camera is not working. Is that right? It's not following.
Oh yeah. Sometimes it's delay. Sorry, yeah.
So I don't know if it captured any of this here.
It's now. It did. Okay,
so,
sorry.
Anyway, so there is a relation, of course, here. You have X, then you have a relation from between X and O, and of course, that thing here doesn't really know anything about X anymore. It's completely independent of it, which is why it's gauge invariant. But you can interpret this. So the relation between X and O is given by R, but it's a field-dependent relation. So you can view this, the interpretation of this thing here, as the measuring A, or components of A, because A will be a tensor, so it will have many degrees of freedom inside, but really measuring components of A at the dynamically defined event in space-time where the reference frame has values O. Okay, so where the reference frame at the point x in space-time, where the reference frame, when you write it in coordinates, where the reference frame is in local configuration little O. Okay. So the crux is that you're defining the space-time event in a dynamical way, right? So usually when we think about tensor fields in space-time, and then we just write them as a function of x, and x we don't think of a dynamically defined event, it's some background event. But due to diffeomorphism invariance, these background events have no physical significance because I can apply diffeomorphism and map that point x to f of x, and it has no meaning. So and physics should be invariant under diffeomorphisms, of course. And now the way to get around this is indeed to say, well, I don't take any background events. They have no physical meaning, but I can define events in a dynamical way. And I define the event in the way that I say, the point in space-time where something happens, and in this case, it's where the reference frame reads so-and-so, where it's in a certain local configuration. Or maybe where a supernova goes off or something like this. So let me maybe just highlight that here. So O, A, R, okay, let's put it in here, phi, and then O. So O in this orientation space. This kind of measures A at event in space-time. Where the frame R is in local orientation. So at event X in space-time, where the frame R is in local orientation, R phi of X equals O. And it's important here that phi, that it's field dependent. Okay, so really, what are dynamic reference frames in gravity? They're nothing else than field dependent coordinate systems, gauge covariant coordinate systems. Okay. That's then how you get that you can write, push forwards, gauge covariant objects to invariant objects on this orientation space. So I'm just thinking what next. So I guess we should discuss reorientations at some point. Maybe I should also give you some examples of how you can realize this. Maybe I'll give you first an example and then discuss reorientations after that. So also, okay, what I maybe goes a bit down here is that this, what I'm describing here, is again a relational notion of locality, okay? Because I'm defining locality now in terms of dynamically defined events, right? So I'm evaluating this tensor field A relative to the reference frame when it's in a certain configuration. So what I mean by local, this O here is defined in terms of a dynamical field. Right, so these R of phi's, they're a set of scalars, really. They transform like a set of scalars. And here, all I've told you so far is, okay, it depends on the field configuration, so somehow I have to build this R out of the fields you have. So it's not some, it's just a general concept, but somehow the field content that you have in your theory has to be enough to build this.
Can I think of phi as kind of like a field on the worldsheet, whereas O is a target space?
It's very theory.
Yeah.
Can I think of words again?
I mean, like just trying to make some analogy. Something.
Yeah. Okay. So probably you could do that. I guess your.
So O is a target space and Y is a.
Yeah. But I mean here I'm not thinking of space here as we general any general covariance theory. So okay. I mean I don't know. I guess for those that are not gravitational physicists here, I've assumed that you know that the space-time diffeomorphisms are gauge symmetries of gravitational theories. If you didn't know that, well, that's the whole reason I'm talking about diffeomorphisms here. So that's really the conceptual difficulty of general activity and other general covariance theories. This general covariance, invariance of covariance really of the physical laws under arbitrary changes of coordinates that amounts to an invariance of the theory under diffeomorphisms. These coordinate changes are essentially diffeomorphisms. So on arbitrary diffeomorphisms, it shouldn't change anything about your theory, the physical state of the theory. Okay, you can see then that, for instance, the Einstein action is invariant under diffeomorphisms. Okay, they correspond to degenerate directions that you have to factor out in your phase space structures and so on. It's basically the same as in standard gauge theories, but the real core difference that makes this so much more difficult in gravity is that diffeomorphisms don't act locally. Right? So they take the point in spacetime and map it to some other point in spacetime. Whereas in gauge theory, local gauge transformations act locally at each point. They don't do anything to really transform. And so that means because gauge transformations in gravity move spacetime points around, you have to start rethinking what you mean in a gauge invariant way by locality. So you can't use the background locality because that's not gauge invariant. And basically what I'm describing here is a gauge invariant way, which you can see about locality, which is, let's say you define it in a relational way relative to your dynamic reference. Okay.
Excuse me, just in case, and if I don't consider dynamics of the gravity and the what changes, like just in fixed curved background space-time, but when the matter field only is dynamical, and the what part would change.
Well, in that case, you would normally not have diffeomorphism invariance in terms of as a gauge theory, right? So you would just have, I mean, you're not in a general covariance setting then. So you can, of course, take some field theories, also in Minkowski space, and parameterize them to make them artificially diffeomorphism invariant. So diffeomorphism invariance or general covariance is not strictly tied to gravity.
Oh.
So parameterized field theories is a counterexample. But yeah, in parameterized field theory, you can do the same thing. Okay. But then it's just that the same construction will apply in that case. So in this paper, we also describe parameterized field theory.
Then this right-hand side is not a special property of the gravity dynamics.
I mean, yeah, this is relevant for any general covariance theory in the sense of where diffeomorphisms are gauge symmetries.
Okay.
But of course, the ones that we are interested in are all gravitational theories, and parameterized field theory is a little bit of a quite model.
Okay.
But yeah, in general, we care about that.
So in that sense, a string action can be applied.
Okay, yeah. So the worksheets action is all needs to be also.
Okay.
But shouldn't, I mean, like the space-time and the orientation space do they need to have the same dimension?
No. So I mean, okay. So if I want to have use them really as a coordinate system in the way I described it, yes, because I want to distinguish in terms of point and orientation space. I want to label points in space-time in a dynamical way. But in fact, you can do something more general than what I'm describing here, that we also described in here. A priori, you can. We actually in that paper we don't start from the reference frame being a map from space-time and the orientation space. We do the inverse. So you can define an orientation space that can be of a much bigger dimension. Maybe I'll explain that. Yeah, maybe I'll explain that now in an example. And then so you have a many-to-one sort of over-complete.
So it doesn't have to be bijection.
Yeah.
Is that what you say?
So, but then it goes from the orientation space to
right.
the that doesn't have to be bijection, but then I can restrict it to some, I can fix some parameters. Let me maybe explain that.
Okay.
So then, okay. Yeah, one thing that maybe I want to say is that this construction of gauge invariant observables here. This is of course really the gravity analog of these frame dressings that we had in special relativity. And one thing that we also show in this paper is you recover all previous constructions of, at least that we know of gravitational observables. Particularly this whole address observable business, relational observables from the canonic quantum gravity community. So this is a covariant description here, but you can map it down to the AEM phase space and then recover the Akaditris power series. And then there exist also these other representations, especially from the Santa Barbara group, Giddings, Merrill, and so on, that we see the integral relational observables and multi-integral observables, and you can get them all in this construction. So it's really a completely general description. And except that, you can generalize it to quantities that are not gauge covariant. So you can have gauge invariant versions of the Christoffel symbols or something like this. So you must do that. The addressing is a little bit different than this one. So I just wanted to emphasize that. So it's actually, there's also a point where you see that really this dynamic frame perspective has a really unifying character. Really, all these different previous approaches to relational observables, to gravitational observables, new concepts of this. So that's I mean, it's not obvious from what I'm saying here, but you can check it out.
Excuse me, what is the difference from this construction and the cross product
Okay,
construction?
yeah, so the cross product was, we only took care of the single diffeomorphism, but here we're taking care of
Or
all
yeah,
So I mean here, of course, I'm assuming when I said H covariance, I mean I wrote down some F, but I meant of course for all F.
yeah.
So here, when I say H covariance, I mean, here I mean this for all F, as in small diffeos. And likewise, when the gauge covariance of the frame that I deleted, I wrote it down for one F, but I mean it of course for all small diffeos. So it's again like in the gauge theory case, it's an infinite dimensional group. So this is an infinite dimensional deparameterization that we're doing. So you can actually, maybe one more thing to say about this here is that you can think of this here as a local deparameterization of your gravitational theory, really as a local special covariantization of your general covariant theory. So when I say special covariantization, what I mean is, so you have gauge symmetry here, there's no more gauge symmetry here, and you could do this, of course, now, well, I'm getting to that. That basically the choice of reference frame is not a gauge choice. It's really it's a convention, just like choosing a Lorentz frame in special relativity. It's not a gauge choice, it's just a convention. And the same will be true here.
So then, if we can quantize this construction, then what algebra, what type of algebra?
Yeah, well, that we don't know yet. I mean, it's just because for that you would. So the thing is, the tools that I'm giving you are kind of tools, but then if you want to apply, you have to give me the theory, and nobody has a quantum gravity, right? So I mean, what you can do is you can, of course, do this in perturbative quantum gravity. Okay, then with this you'll recover, for instance, constructions by especially Steve Giddings in Santa Barbara. He's looking at trust observables in perturbative gravity. It's all consistent. He doesn't really look at algebras. I mean, specifying what exactly the algebras are, but I wish we could do that. Just, I don't think I can give you a nice answer as in what's that algebra features. I mean, there are, for instance, also Harlow and Wu looked at algebras of diffeomorphic observables in JT gravity, and all that can accommodate with this. So example. So let's do this kind of geodesic dressing to boundaries that people will usually do in holography. It's kind of a nice example. Maybe that some of you guys are familiar with. So this here is now our boundary, EM. And I have a boundary anchor point, let's call it Z. I'm going to shoot in the geodesic somewhere. And then, I can have here my W, that's a boundary vector field that tells me what the direction is in which I shoot in the geodesic. And let's take tau to be the distance. It could be a time like geodesic to go up in space, like whatever. So then we can say this is a point X, and it depends really on W, tau, and Z. Okay? So where I end up in the bulk depends on what parameterization I choose here, and of course, because it's a geodesic, particular depends on field configuration. And so it will depend on the metric. Then if I have other degrees of freedom in my theory, the metric couples to them, and they are dependent. And now, so people usually just look at single geodesics, but really what you should be doing is looking at whole congruence of them. So it's going to be a disaster if I draw them all, but I hope you get the idea. So look at a congruence of geodesics. So that I can, for a neighborhood on the boundary, for each point, I have one geodesic that goes in a specific direction. And in order for this to work as a dynamical coordinate system, it really has to be congruence without cost. Provides a bulk parameterization for n, so it's the neighborhood that I had put in the definition of the reference frame. I will highlight that this neighborhood depends on the field configuration. Where we have no caustics. So if the geodesics cross, then I'm in trouble, of course. And so where they will start crossing, that will depend on the field configuration, obviously. So that tells you already that in general, of course, these field-dependent coordinate maps or these dynamic reference frames, they'll be local in a twofold sense. They will be only defined just like any coordinate system in a local region in my space-time. And in general, they will also only be defined in a local region in field space. Okay? They may not be well defined everywhere in my field space. So you have to be mindful of that. So okay, well, I haven't really defined R yet, so maybe I shouldn't write that yet. I hope you get the idea of what I want to say. So then now what we can say is, so this W, tau, and Z. So we can say that they parameterize, let's call it O bar. Okay, so that's you can call it an orientation space. So in this case, suppose we're in 4 dimensions, so that means Z is 3 parameters, this is 1 parameter, that's another 3, so I have 7 parameters. So I have 7 parameters for parameterizing a bulk region of 4 dimensions, so it's of course over complete. But really what we're currently doing is, we're basically mapping from O bar. So at the moment we're going from O bar into M using this here. Okay? So now I can say, well, suppose in this boundary in this region on the boundary, I'm going to fix the boundary vector field W in the boundary that determines the initial direction of the geodesic into the bulk. So suppose we fix W. Did I say that this is a boundary vector field? And you could, so boundary vector field must be tangential to the must be tangential to delta m, but then the initial direction you can define in terms of the normal of the boundary. So the initial direction will be given by W and the normal to the boundary. But I'm suppressing the normal. So so if I fix this, then I fix 3 parameters, and then I'm left with 4 parameters. So then I have tau and z. So it's 4 parameters for a 4-dimensional space-time region. So then we have tau w, so z are free, and so the subspace of w fixed, but letting these run. So this will parameterize my choice of O. This will be the orientation space I'm going to be interested in. And now, as long as I have a congruence without caustics, I can guarantee that for some neighborhood, the map from tau z into the bulk will be injective. And for that region, I can actually invert this map from tau z into the bulk. And the inverse of that map, that's the dynamic reference frame. Okay.
Excuse me.
Yeah.
So is it the trivial that fixing W like that, you can reach any point in the bulk?
No, in general you cannot.
Cannot, right?
Yeah,
Okay.
This may not be a good description for every single block. It's just, there will be some region such that, it provides a good parameterization. So, the point is really these dynamic reference frames that provide you coordinate systems. The only difference to the static case is that these coordinate systems are gauge covariant, so they depend on the field configuration. Otherwise, they're just coordinate systems, so in general, you kind of expect that they covariate. So that's not a problem. But yeah, so the point is you can, they will exist. So basically pick n5 such that, I don't know how I call this map now. It's not hard to, there was something from O to N. That is injective. So then you invert this on the image, and then you get R5 basically is R tilde by inverse, and this is going to be a map from N phi to O. Okay, so now, this you can do. Now, of course, you have to check that if I define it in this way, that I actually have to satisfy gauge covariance. Okay? And so that is a non-trivial check. We show that in this paper, it actually does obey gauge covariance. So, that's proven in this paper, in the warm-up. So this is actually the warm-up example of that paper. So it's not a very technical discussion of this. The proof is not very complicated, but probably takes about 10 minutes or so, which isn't much. So you can show that this is gauge covariance. Meaning, R star phi. And in particular, that transforms like scalars. That's important. So the reason this is true is that the geodesic equation is a tensor equation. It's a covariant equation, and everything is defined in terms of covariant objects. That's why in the end we get some covariant. That's essentially the intuition. And so this is the step that people usually don't do. Okay? So they don't convert this to real, so in the high energy physics, people don't usually do that. And then, but the point is now that, so abstractly you can show that this is true, but really, what does it, so you get something that transforms like scalars, and what are you doing? So you're taking space-time point x, and you're inverting this relation for fixed w, so you're mapping x to tau z. Okay, so really what our phi does is it really takes so x in this neighborhood depends on phi, and it maps it to tau and z. And so this you can convince yourself then this is equivalent to scalar fields. I should say metric constructed, or really field content dependent scalar fields. We can write it as tau phi of x, and it'll be, tau that is associated with x, and that's that I of phi, and this gives you that I of x. What I mean by this is that this description for a fixed field configuration, a specific tau z will fix an x. Okay, the relation will change as I change the field configuration. So really, what I'm doing is I'm just inverting it, so you can show that the map that to each the inverse to the bulk points associates the tau that for that field configuration is associated with x, and these guys that associate the boundary anchor point coordinates with that bulk point for the given field configuration. These are scalar fields. So it means in particular they transform in this way here. Each of them transforms in this way. But really, when I write them as scalar fields, I mean they are composite scalar fields, so they're built in a composite way out of the metric and all the other degrees of freedom. Or actually the metric. And in particular, because the geodesics are non-local, so they're not locally constructed metric-dependent scalars. Okay. So that's one example. So just like in kind of zillions of coordinate systems, continuum of coordinate systems, you can also build continuum of dynamic reference frames. Let's just give you one impression of how we can do it. So this here is really using metric degrees of freedom to build a reference frame, but you can of course use matter degrees of freedom also, and there's a lot of toy models. So another example, for instance, is a kind of simple example is brown Fukash dust. So I'm just mentioning this, not that these two are kind of sort of exclusive examples, just that they're particularly simple examples, and they're kind of well known. This one is canonical gravity, really well known. So what do we do here? We used a spatial boundary as an anchor point for geodesics, and then we parameterize the bulk. And brown Fukash dust is slightly dual to that. You have some Cauchy slice in your bulk of the spacetime, so you don't even need an asymptotic boundary. And you have dust particles, so they're dynamical degrees of freedom in your theory. And it turns out that so you have a congruence of dust particles. And on solutions, these the world lines of the dust particles are geodesics also. So that's spatial boundary anchored geodesics, and these are Cauchy slice anchored geodesics. And it turns out that they give exactly the same kind of thing. Okay, so you can the dust field degrees of freedom, they also define scalar fields. And this is Cauchy slice So maybe let me leave it at this for the examples. Are there any questions on this? Still need to tell you something about the reorientations.
Excuse me.
Yeah.
So basically, this idea is on shell idea. I mean, so after solving the equation motion completely, then we can construct the quantity.
Yeah. I mean, it's really all done up. I mean, some of the construction you can do at a kinematical level, but at the end of the day, of course, you do it on shell. That's what we care about. Because one thing is, especially in the covariant phase space, gauge symmetries are on shell, not off shell.
Oh, okay, I see.
Hamiltonian and diffeomorphism constraints are secondary,
Mhm.
so you need to have the correct motion.
Yeah. I see. So, and you have a quantum version of this argument? Something?
Yeah, at some level, yes.
Okay.
So at a formal pathological level, yes.
Oh.
Let me maybe first tell you something about reorientations. One thing I should definitely tell you before I go anywhere, I should tell you about reorientations and frame changes, right? So I forgot to tell you about frame changes in the gauge theory case, but you know it works in the same way as you should basically guess by now.
Mm-hmm.
If you guess it, and you paid attention, that it will be correct how it works. But you know, in gravity it's maybe a little bit more interesting, so I should tell you about that. So and then maybe I'll finish on that note. But even when you think about this, clearly somebody must guess correctly what the frame changes will be, but just doing coordinates, or it will just be coordinate transformations. Good. So now let's do reorientations. And wow, okay, yeah, I guess I'm writing it down, but I do too, I guess you know this by now. I should write it down, I guess, because it was also the other way around. But really, this is an SO3-1 transformation on the orientation space. Right? So now we have R phi from some neighborhood into the orientation space. We discussed the diffeomorphisms that act here. So what's missing is the diffeomorphisms that act there. So the diffeomorphisms that act here are the analog of these frame reorientations. So they only act on the image of the reference frame, just like that happens here. So now it's goes on O, and what F tilde, okay, so F tilde O, so then F tilde. They just use the same kind of notation that I used before in the gauge theory context. So it's still legible, the pen is starting to wear out. And this is just F tilde R. So it's just a diffeomorphism that acts on the other side of the reference frame. So it's the same kind of structure that we saw in gauge theory. Gauge transformation acts on one side of the frame, reorientation on the other side. Similarly here with the tetrads, one act on the pre-image, the other on the image. That's the same thing. And again, this is something that a priori only acts on the reference frame and not on anything else. Because before I address anything, nothing else will know anything about the image of the reference frame. Will know anything about orientation space. So it should also leaving other fields invariant. Then you can again ask, how do I realize something like this? And so finite region realization is maybe again the simplest thing. There's other ways in which you can do it, but you know, we have our finite region like in gauge theories. And suppose we have somehow, again, some asymptotic boundary, delta M, and we shoot in geodesics rather than Wilson lines, or gravitational Wilson lines really, also to define what we mean by the subregion in a gauge invariant way. You know, then again, like before, I can do, for instance, large gauge transformations here, or some other kind of transformations, physical transformations to the initial data in the complement of the causal complement of the subregion. So I would change the Wilson line configuration without doing anything to the bulk here, and that would guarantee me that I have something like this. Okay. So that's again a way that you can think of reorientations. Now, okay, I guess we're now done in principle. Let me just do the frame changes and then I can finish. I think that's still an important part. And remember we have these two ways of doing it. And I'm just going to do the gauge invariant one now. This was this lambda AB prime given by EA mu tilde E prime. Remember? So then there's the gauge equivalent or the gauge fixed version of this. But we're transforming, we're doing a Lorentz transformation by a amount that's given by the relational observable relating the two reference points. So it'll be the same thing now. So we have now, call this O1, that's our O2, and here's our space-time M. R1, R2. Now suppose they, the reference frames, they have a joint domain here. So it will correspond to maybe some region here or something like that. So then it's of course meaningful to ask how do I represent this region with respect to that frame and that frame. And well, you can guess that it's going to be the same thing, right? So what I'm doing is space. So yeah, for R1, 2, we'll highlight that it was field dependent. So it's from O1 to O2, and well, just given by obvious things. So I'm doing R2, my encapsulated with R1, my inputs. And then, of course, on the joints domain, right? So if I'm writing O1, O2, it may not be defined at all for O1, O2, but you know, it's just standard for transformations. But the crux is that it's field dependent. So you know, it's the same compositional structure. Also, you see this reference frame and all that stuff. So it's basic kind of stuff. And now, now we can think a little bit about this. So what is this thing here? It's really, you know, it is again a diffeomorphism, but by an amount that's given by the relation between the two frames. Because, you know, this is a gauge covariant one, so it is a scalar, a set of scalars, and this is a set of scalars. So really, this is R1 phi push forwards of R2 phi. So this is R2 addressed with respect to R1. So this is the relational observable describing R2 relative to R1. So that's really a side analog here. And it's a diffeomorphism if we assume that these maps individually are diffeomorphisms. So then we're doing a diffeomorphism from O1 to O2 by an amount given by relation also to reference frames. So that's exactly the same thing. So there with the analogous. And then of course you can now maybe that's the last thing I will write down. This SR case that we had S U, and then we addressed E to A to the prime. So you get SA, you get E prime tilde, and then you have this lambda over E prime in between. And so what's the analog of this? So this is just the map between these orientation spaces. So and now for relational observables. So what we want to do is, we have the relational observable describing some space-time H covariant quantity relative to reference frame 1. So we just take this map R1 to 2 and push that thing forward. So we have R1 to I, and then we push it forward, and then this is just nothing else than OA relative to R2. Fine. So it's really the same thing. Okay, so I'm here, this transformation to go from this to that, I'm taking this relational observable, I'm dressing it with, I'm doing a redressing, so I'm transforming this observable into a large transformation corresponding to the frame relation. And the corresponding thing here is I take the relational observable and I do the diffeomorphism on it corresponding to the frame relation. It's pushed forward as a diffeomorphism. But then that this is true, you can just, is that clear? I mean, this is, here you're just using that this is R1 by A. And this here, if you look at the definition, this is R2, R1 inverse, right? So then you see, so this is R2. So that's the, maybe the rest are just same words, but so you see, what you can now have is really, you can have gauge invariance, but frame covariance, also in gravitational theories. Okay. So usually when we think about coordinate descriptions of tensors and so on, or the covariance of the Einstein equations, we describe them in some fixed coordinates or in some coordinate system. And then we do some change of coordinates, and then the claim is, the Einstein equations are covariant under frame changes, but really when I look at the individual tensor descriptions, it's we're not dealing with gauge invariance, so we have a gauge non-invariance and frame covariance. This allows you to now make this a little bit nicer by going to the statement that you have actually gauge invariance and frame covariance at the same time. And of course, I have to describe that. But, this A here, for instance, it could be the Einstein tensor, or the tensor corresponding to the Einstein equation could be, Einstein tensor minus the stress energy tensor. And then this here, maybe I should still say that. So we get relational UOMs. So for example, so A is E, where E is the tensors corresponding to your equations of motion, and O of E. So this here is like EOMs, okay? So they come as tensors. Then OE of R1 is a gauge invariant. That frame covariance description of the equation of motion. So it's dress the equation of motion. And then we just do the change of the covariance under these kinds of gauge transformations. Okay, so this puts really this notion of general covariance, in my opinion, on a somewhat arguably nicer footing, that you don't have to talk about anything unphysical. It follows from the usual notion of gauge covariance, from the usual notion of general covariance. It's not independent of it, but it puts it in a somewhat nicer form. Right? So then it really makes clear, it makes sense, that as long as you include internal reference frames or really dynamic reference frames, then you can make all the usual discussions really completely gauge invariant. And of course, so far I've only discussed gauge invariant description. You can of course now go and gauge fix any of this. I mean, as usual, by the equivalence of gauge fixing and then gauge invariant description. When you gauge fix, you know, then these frame fields, for instance, they may look like a field independent coordinates. So yeah, you know, the equivalence with the gauge fix description that follows also as in relativity. And also you can use these constructions to also, what I did in gauge theories with edge modes, you can think of them as reference frames. The same thing applies also to gravitation space. It's also something that we worked out in a paper. So the interpretation of the work on. Now coming to your last question, can we quantize this? Well, you know, this is pretty general formalism, and rigorous quantization of it is a little bit difficult, of course. But at a formal level, you can do something, and you can use a classical formulation. So path integral, in some sense, just stuff classical, you know, formalism inside. Of course, you have to somehow specify what configurations you integrate over. That's maybe where the more subtle part is, but at least in the other, like action and so on, and measure inside the path integral, and just use these classical descriptions. And what you can do is you can, in the path integral, you can use these reference frames. And when you take the field space as really a bundle, principal bundle, these reference frames allow you to do a natural splitting of the field space degrees of freedom between the horizontal and vertical, and in particular also the field space metric that goes into the definition of the measure of the path integral. So you know, they give you a natural fiber adapted coordinates, and when the field space metric is gauge invariant, it actually turns out that the field space metric nicely goes into block diagonal form on the fiber coordinates and the gauge invariant relational terminals. When you do this, then you can completely factor out the fiber part, the gauge non-invariant part. It's of course divergent. You just throw it away, and then you just take the remaining part, which is the purely relational terminal part, the gauge invariant part. And that one is completely frame invariant actually. So you use a frame to define it, but then you can show that the passive is the same with two different reference. But it's a somewhat formal construction. And then the idea of this is, for instance, to use that for effective actions and normalization. Anyway, I think I shall stop here. So thanks very much for keeping until the bitter end. So